Today we're gonna talk about the calibration methods, and sort of I've mentioned about this quite a bit before. Now remember, there are three types of calibration methods. There's what you refer to as external calibration method, is what you call a standard addition calibration method, and there is internal standard calibration method. Now, it's good for you to understand the advantages and disadvantages of each of these methods so that you can choose the appropriate calibration method, depending on the analytical problem in question. So the easiest type of calibration method, which I'm sure you guys have come across before, is the external standard calibration method. And this is where, just like you did with spectrophotometric determination of ion lab, the very first lab that you guys did, you will find that you created the standard solutions and you analyze them separately, from your unknown, so the standards are prepared and analyzed separately from the unknown. And you're going to realize there's a problem in doing that. The standard addition method, on the other hand, is where you prepare the standard and actually spike it inside, the analyte or the unknown, and then you analyze the sample, at the same time. So the standard is analyzed in the presence of the analyte. And lastly, the internal standard method, and I'm going to explain it a little later, it's where you spike an internal standard, which is an analog, a chemical species that is very, very similar to your analyte, but they are distinguishable. And I'm going to explain, why you have to do all these different types of methods. So first, let's start with external calibration method. As I've said, you prepare the standard solution and then you analyze it, differently or separately from your unknown. And then you generate, the linear regression. And from the equation of the line, as you well know, you can determine the unknown from the regression line, because when you analyze the unknown, you have the y, and so you can determine, what the x is. Now, the problem with the external calibration method is because you assume that the instrument is gonna respond in the same way for the analyte as well as for the standard. And that allows the assumption, because remember, the analyte typically is in the presence of a lot of matrices when you're working with an unknown. And as we well know, matrices interfere with the analyte of interest. But for the standards, you just prepare them in a neat solvent, and so you don't have any matrices at all. So you can see, a big problem making that assumption. And so some of the factors, that limit the external calibration method, though it's the easiest method to do in the lab, but it's not the most ideal, is the fact that the matrices in the sample interfere, with the analyte response, and that's a problem. Now, also remember, you're making an assumption that the instrument, it's in the same codation, at the time when you're analyzing the blank, when you're analyzing the standard, as well as when you're analyzing, the sample. But as you're going to understand, instruments fluctuate, they are always in a drift. And so they can drift, based on the temperature in the room. They can drift, based on the electrical, environment, that they are in. And so it's not a very good assumption, that the conditions of the instrument are exactly the same, though you're analyzing, the standard separately, from the sample. Now, another major limitation of the external calibration method is because you're making an assumption, that when you're doing the sample preparation, that will not interfere, and that's not a good assumption either. Also, you're making an assumption, of potential systematic errors. Assume you took the sample through different steps compared to the standard. Remember, lots of things could happen because you're dealing with a chemical that can undergo vaporization. Some of it could get lost. It can undergo other chemical, reactions, such as oxidation if you expose it to air and so forth. And so because of that, you may end up losing, a bit of the sample as you take it through all the different steps, of sample preparation. And so that one is not accounted for, in the external calibration method. Now remember also, there are random errors, that are associated with generating the calibration graph. And so because you're doing the analysis of the sample and the standards at different time, then you don't have any correction, because of that. A better method, of doing calibration in analytical chemistry is actually standard addition calibration. Now, this is how it works, and it largely corrects, for matrix interferences. With standard addition calibration, you analyze the sample in the presence, of the standard solutions. So how do you do this? You typically prepare the standard solutions, and then, you typically take the sample, you typically take the sample, and you would spike it with increasing amount of a known standard, okay? And then after that, you would make it up to volume in a volumetric flask. So I say this again, so with standard addition method, one way of doing it is you take the sample, say 5 ml, you put it in each of the volumetric flask, and then you spike each of the volumetric flask with increasing volume of a known standard solution. For example, vial number 1, you can spike it with 0, with 0 volume of your standard solution. Vial number 2, you spike it with, say, 5 ml. Vial number 3, 15 ml, and so on, all right, of your standard solution. And then after that, you make it up to volume. And then you can do the analysis, using the analytical instrumentation in question. See what we have done. In each of these volumetric flasks, you've got a known concentration of the standard that you spiked, but you also have a known volume of the unknown sample in each one of them. And so the matrices in each of these solutions are the same. And so if you inject it into the instrument, the effect of the matrices, gets corrected, because the analyte is being analyzed in the same environment, as the matrices. And so you generate, the calibration graph. And remember again, the calibration graph, as always, it has to be linear, for it to be used, analytically, to do quantitation. Maybe the question that you have is, well, in this environment then, how do I determine the concentration of the unknown from my calibration? That's what we're going to talk about, in the next slide. Now, the standard addition equation that helps you determine the concentration of the unknown is as follows, okay? So you've got the analyte initially present, and then you've got the signal from that analyte. And then these one you divided by the ratio of the standard solution that you spiked into the volumetric flask. And of course, remember, you spiked it in the presence of the analyte, which is the unknown. And then after you analyze this, you get the signal. And so this is what you refer to as a standard addition equation. And you actually can use it, to determine the concentration of the unknown by the so-called single point calibration. So you can actually just have one standard spiked, rather one analyte spiked with the standard, and you can just use that single standard, to do your calibration. I'll give you an example, of a single point, calibration. You can do it. It's not ideal, but it can be done, especially if at all you are very limited in the amount of standard, that is available. Take an example of this. You've got a blood sample, and then you take a serum from that blood sample, and then you've been asked to determine the concentration of sodium ions in that serum sample. And possibly in this case, you're using potentiometry. So the signal that you get from that serum sample, is 4.41 millivolts. Okay. Now, after that, you take 5 ml of a standard solution that is known, 2.08 molar of salt, and then you spike it into 95 ml of your serum sample. And after that, you do the analysis, and it gives you a signal of 7.82 millivolts. You can see what you really need to do is to substitute all these values into the standardization equation. Maybe the caveat that you really need to remember is the following. Take account of the dilutions. Take account of the dilutions. So you can see, the analyte initio, I don't know what that is, but I already know, the signal that I got, and that's what I put here, the 4.41 for the neat serum sample. And then I need to determine the concentration of the spike because I did the dilution, okay? And, the concentration of the spike, maybe that standard final, it's gonna be equals to, the standard that I had initially multiplied by the dilution factor, which is the volume added divided by the volume total. Now, we already know that the standard here is equals to 2.08. And so times the volume that was added is 5 divided by the volume total is 100. All right, is 100 mil because you had 5 mil plus the 95 mil. And so if you calculate that, you're actually gonna see the concentration, of the standard final is 0.104, and that's what you put, right there. That's what you have right there. Now, the analyte final, on the other hand, remember, equally you did a dilution, so the analyte final is equals to analyte initio. I don't know what it is. That's what I'm looking for, times the dilution factor. And the dilution factor in this case, initially I had 95 mils of the serum divided by the 100 mil of the serum. And you can see, that's what I put in there. So looking at my equation then, I've got only one unknown, which is the analyte initio, which is the sodium ion initially present. And using, of course, simple algebraic, computation, you can just calculate, what this is. And I hope all of us, know how to do that. And so the sodium initially present, is equals to 0.126. Molar concentration. So that's what you do for standardization where you're only doing a single point calibration, meaning you've got only one standard solution, that has your analyte present. Okay. Now, however, you're gonna see in most cases you really wanna do multi-point calibration, because that one is more robust. It's more robust analytically, if at all you've got multiple standards, that you've analyzed. As you've seen before, ideally in analytical chemistry, you want to analyze something multiple times so that you can have a high degree of confidence. And that is why we often do multi-point, calibration plots. So how do you do determination of the unknown for the multi-point calibration method when you're doing standardization? Okay, so you typically use these equation. It looks ugly, but it's actually not very difficult to see how it works, and I won't go into the derivation of this, but as you can see, typically you would have the signal in the y-axis, and then you'll have the concentration of the different standards in the x-axis. And of course, you already know how to do that. If you spike something, you can calculate its concentration just based on the simple dilution formula. C1 V1 is equals to C2 V2, and so you can generate the standard for each of the standards that you've actually prepared, and then the corresponding signal is plotted in the y-axis, whereas the standards are plotted in the x-axis. And then you would do the equation of the line, y is equals to mx plus b, which you can easily get from your Excel spreadsheet to create the linear regression. Okay, and you would do an extrapolation, where you get y is equals to 0, so that you can extrapolate this line until it touches, the x-axis. And so that interpolation here is actually equivalent, to the concentration of the unknown. All right, so you can do it graphically, but I think the easier way is just to make y is equals to 0, in your equation of the line. Y is equals to 0, and so x then is gonna be equals to minus b divided by the m, and so this one would be the concentration of the unknown, in your volumetric flask. So that's what you do for the standard addition calibration. Okay, now take note of this. You already had done some dilution, okay, because you took the unknown, you added the standard solution, and you made it up to volume. And so because of that, typically you would take the signal and you would multiply it by the concentration factor so that you can work backwards to what you started with. Okay, and so that is what you would do, for the y-axis. And so the intercept here then is actually going to give you the concentration of the unknown if you do this. Hope that's clear. So that's approach one. But there's another approach where the x-axis remains exactly the same, meaning you calculate the concentration of the standards in each of your solution. Same way, concentration of the standard initial multiplied by the dilution factor, which is the volume of the spike divided by the volume total. And I think all of us know that. Okay. And then in the y-axis, you can decide to just simply plot what the instrument spits at you in terms of the signal. Okay. But whatever you get then as the intercept here, when you get the equation of the line, y is equals to mx plus b, and then you make y is equals to 0 so that you can get this intercept. And so x is going to be equals to minus b divided by the slope. And again, remember, we only care for the magnitude, so just ignore the negative sign. Okay, and so the number that you get in this case then is actually going to be the x final, or the analyte final. Now the analyte final has not accounted for the dilution. And so to get the X initial, which is what you are interested in, the analyte before the dilution, is going to be equals to the X final, which is just this intercept, multiplied by the concentration factor, which is the volume final, divided by the volume that you initially had. Meaning, for example, in the problem that I had before here, where you took 5 mil, of your unknown, and then the total volume assume is 50 mil volumetric flask. That means that the concentration factor in that case is going to be equals to, the 50 mil divided by the 5 mil. Okay, so that's a concentration factor, meaning this is the V final divided by the V initial, which is the amount of sample that you actually added. Okay. So if you use this approach then, where you didn't take into account the concentration factor, for the y-axis, remember you have to take account then of the concentration factor, for the x-intercept, which I've already explained. You get it from make y is equals to 0 of your equation of the line, get, minus b divided by the m, which is the calibration sensitivity. You get the xf multiplied by the concentration factor, which is the total volume of the solution, divided by the volume of the analyte that you added into each of the volumetric flask. Okay, so that's the next approach, of doing multi-point standardization calibration. But there's another approach, that I think it's even easier. All right. So in this case, the y-axis remain, what the instrument spits at you in terms of the signal. However, the x-axis, instead of plotting, the concentration of the standard, simply plot, the volume that you added into each of the volumetric flasks. So take note of this volume, say volume in mils, that you added in each of the volumetric flask. Okay, and you do the calibration and it's gonna be linear. Okay, now when you get the equation of the line y is equals to mx plus b, you get the intercept, the x-intercept, y is equals to 0, and so the x is gonna be minus b again divided by the m, and remember we only take the magnitude of that. But remember then, this is gonna be in volume because the intercept here, it's in actually volume. So how do you get the concentration then in the units of concentration such as ppm? What you do is you take this number in volume units multiplied by the concentration of the standard that was spiked, in each of the volumetric flask. Remember, this one is gonna be in concentration units, or maybe ppm, but then again divided by the volume of the unknown that you added in each of the volumetric flasks. So the volume that you initially added. In the problem I gave before, that volume, was 5 mil. So as simple as that. And then the concentration of the standard that you spiked, of course, that. And whatever you get then is going to be in concentration units, and that would be the concentration of the sample, that you analyzed. So you can see it's a fairly simple method here if you simply keep the x-axis as the volume that was spiked. But again, it's up to you which method you best think that you can use. Method 1, method 2, and method 3, although I think method 3, is much, much simpler. So the next type of calibration that I'm gonna talk about, which is the last one, is the internal standard calibration method. Now, the internal standard calibration method is meant to correct for instrument irreproducibility. every instrument is typically fairly unstable. Okay. For example, if at all you're doing GC, gas chromatography, it's very difficult to inject your sample reproducibly. For example, assume you're doing mass spectroscopy. In general, mass spectroscopy is very prone to environmental disturbances because in the environment there are lots of ions, and mass spectrometry detects ions in its environment. So even if you sneeze at it, it's gonna respond, to that, though there's no analyte that you're trying to analyze. So internal standard method, it's actually meant to correct, for instrument variations. Now, it's also meant to correct, for sample preparation irreproducibility. Meaning, you take a sample and you've taken it through different sets of steps, like what you guys did with the ion lab. You would take the sample and then you reacted it, with bipyridine to get a complex. And you did a series of dilutions. Remember, it's possible to have lost a little bit of your sample due to your analyte absorbing onto the volumetric flask. Now, with internal standard method, you're able to correct, for those sample preparation irreproducibilities due possibly to sample loss, maybe due to analyte being adsorbed onto the volumetric flask, maybe the analyte evaporating if at all you're dealing with analytes with very high vapor pressures, and so forth. So what is an ideal internal standard? An ideal internal standard that you would use, that you would spike into, your standard solutions as well as the unknown. Remember, it should have these properties. The internal standard should be structurally similar but distinguishable from your analyte. The internal standard should respond in a very, very similar fashion, to your analyte as well. The internal standard, of course, should be stable, and it should be soluble in the same solvent, that you're analyzing the analyte in. And lastly, the internal standard, should not react, with your analyte. Okay. So practically, the way you would do this is you would take your standards and then you would spike them, with an internal standard. You would take the unknown and you would spike it with the internal standard. And as I've said, the internal standard that you choose should have all these properties: structurally similar but distinguishable. It should respond to the it should respond to detector in the similar way as the analyte. It should be stable, it should be soluble in the same solvent. It should not interfere or react, with the analyte. Okay. And after that, you would plot your calibration as follows, so the concentration of your standards. However, in this case, for the internal standard method, in the y-axis, you take the signal of the analyte and then you divide it by the signal of the internal standard, and that's what you plot in the y-axis. So in the y-axis, you plot a ratio of the analyte response divided by the standard, internal standard response. That's what you plot in the y-axis. The rest of the thing is very similar to the external calibration method. Now take note of this. As we did before with the standardization method, you can also do a single point, calibration. And the single point calibration is based on single point internal standard calibration is based on this relationship, that the signal of the analyte divided by the concentration of the analyte should be equals to a constant, it should be equals to a response factor F multiplied by this ratio signal of the standard, that is the internal standard, divided by the concentration of the internal standard. when you analyze it using an instrument, possibly GC in this case, you can see that the analytes are distinguishable. Maybe that's your internal standard. It should be distinguishable from your analyte. Okay, hope it's fairly clear. So you can use this equation to do a more single point internal standard calibration. Let me give you an example. Assume you've been asked to analyze caffeine in tea. Okay, and so you prepare a caffeine standard. This is natural caffeine. All right, and then you spike it with an internal standard. Now, the best internal standard that has got all the features that we talked about is typically an isotopic label of that particular compound. So this is the most ideal internal standard, an isotopic label of the analyte. Okay, so you can see in this case you took the caffeine and you spiked it with the isotopic label of caffeine. In this case it will be say caffeine carbon 13. That's how you do isotopic labeling, where you knock out one of the atom or one of the element in the structure and you replace it with an isotope, a heavier isotope of that element. Okay, and that's an isotopic label, and that's how you do labeling. So you can see in this case then you took the caffeine standard, you analyzed it using the GC, and you got a peak of area 350. And then you analyzed an isotopic label, internal standard, of a known concentration, and you got 325. So the very first step then is to substitute these numbers into the internal standard equation so that you can get the response factor. So first calculate the response factor, and as you can see, I just substitute those numbers and I can calculate the response factor, as 0.731 is the only unknown in this case. After that, now you do the real analysis. The response factor, the F, you can do the real analysis. So in this case, the real analysis was 5 ml of the labeled caffeine, remember that's the internal standard, was added to 10 ml of tea sample. You're trying to analyze caffeine in tea. And then after that, you did the dilution, of that spiked tea sample to 25 ml inside a volumetric flask. And then you analyzed it using the GC. Take note of this. You get 450 as your area, for the analyte in the tea. And then you get the 420 for the isotopically labeled caffeine that was spiked in the tea, so you get that. And you can see that you just need to substitute them into the equation here again. You got the 450, that's the analyte peak. You got the 420, that is a signal of the internal standard. And then you've got the corresponding concentration of the labeled caffeine, which is 0.016. Take note of this, account for dilution, right? Because the concentration multiplied by the dilution factor. So the only thing that is really not known is the caffeine, which is what you're looking for. And so after you do the calculation, you're gonna see the concentration is equals to this, okay? But this is a concentration before dilution. And you'll be looking at the concentration of the caffeine that was present in the tea originally. So remember, you have to work backwards. And how do you do that? You take the number that you got right here, which is what you analyzed, but you diluted it. So you need to multiply it by the concentration factor, which is the volume total, 25, divided by the 10, which is what you originally had. And so the answer is going to be 0.039 molar. So you can see fairly straightforward, you're using internal standard, calibration, which corrects for instrument reproducibility or sample preparation reproducibility. That's the purpose for internal standard. Standardization, on the other hand, corrects for matrix effects. So why don't you try this problem at home? It's very similar, to what I've just done in the previous slide. So try that at home. Again, there's a single point calibration, and you're gonna use, you're gonna get an answer of 0.143 if you do it properly. So what are some of the difficulties with the internal standard? Well, one major difficulty is to get an ideal internal standard. Isotopically labeled standards are very expensive, that's one, and sometimes they are not available to you. And so that's a problem. Another big problem, is to make sure that you introduce the internal standard reproducibly in both the analyte as well as the standards. And in most cases, you're spiking very little volumes. And so it's very difficult, to reproducibly introduce, the internal standard, into the standard solutions as well as they are known. And so that adds a little bit, of an error. Okay. And so sometimes it's possible, to actually use a chemical species that's already present, in your sample. All right, maybe an interfering species, and actually use it, as an internal standard. So sometimes people do that in the event, that the internal standard is not available, the isotopic label. If you cannot get the isotopic label of the internal standard, then the next best option is for you to use an isomer, a structured isomer, of your standard, of your analyte. Okay, so if you can get an isotopic label, then go with a structured isomer. So the multipoint calibration curve for internal standard, as I said before, fairly straightforward. The x-axis stays the same. That's the concentration of the standard solutions. Of course, that was spiked, with the internal standard. And then in the y-axis, you just get a ratio of your analyte divided by the concentration, divided by the signal, of your internal standard. And that's what you plot, in the x-axis, in the y-axis. And then the rest, becomes fairly straightforward, just like an external calibration method. And meaning, in this case, when you're doing for determining the unknown, remember the unknown in this case is analyzed separately, again, from your internal separately, from your standard solutions. So you get the equation of the line, y is equals to mx plus b. But you already know, the y for the unknown, the signal for the unknown. And so you just need to substitute it here so that you can calculate your x, very similar, as I said, to the external standard calibration method. The only difference in this case is you take a ratio of the signal. So lastly, just to summarize this, when you're dealing with a large number of samples, and maybe some of you are going to work for labs where you're dealing with lots of samples, remember you cannot make an assumption that the instrument is going to respond the same way in the morning compared to the afternoon. So you always have to check, for the instrument drift. Okay, because the instrument, as I said, can change. The response may change because of the room temperature. Remember also, the analytical method could be affected, by reagents possibly spoiling and so on. And so always counter check, the method drift. Meaning, make sure you analyze a calibration check. So take a standard solution that and analyze it, at regular intervals. Analyze it maybe after every, say, 20 samples. You analyze something that and confirm it's giving you the results that you want. That's what a calibration check means. Also, in most cases, it's good to perform, what you call blind samples, where you're given a sample, you don't know what it is as the analyst, but whoever is giving you knows what it is. It's very similar to what we are doing in the lab. I will give you an unknown. It's unknown to you, but it's known to me, okay? And so that will be a blind sample, and I'm gonna be able to confirm how good your analytical method is because I gave you a sample that you don't know, and so you can cook the numbers, but I know exactly what it is. And so it's a classical way of doing quality control, blind samples, analyzing blind samples at regular intervals. And that one validates, your analytical method is doing what it should. And then finally, it's very important, to always follow the standard operating procedures, which is the procedural steps, that are outlined as the best method, for whatever method that you're analyzing. So make sure you follow the standard operating procedures, as outlined, because small variations, can cause a lot of differences in your final results. And so this one is classical. This is what you typically do if you're ever hired in a high throughput, lab environment where you're analyzing so many samples, throughout the day. And so again, you have to do the assessment, to verify, that the data that you actually get, is very, very accurate, which means it's very, very close to the true value. And so that's the purpose, of a control chart. You know the true value. And so you want, the data that you get to be distributed very, very close to the true value. If it is away from the true value, maybe plus 2 sigma standard deviation, then there's a warning sign. That's a warning sign that maybe there could be a problem with your analytical method. Maybe there could be a problem with your instrument. Maybe there could be a problem, with your reagent and so on. And so you have to stop and find out what the problem is. Okay, so that's the purpose, of a control chart. In the industry, they typically use a control chart to confirm the analyst is getting reliable data, and you're able to confirm, what the problem is if there's a deviation, from what is expected. So I've given you a template, for you guys to use for your labs, an Excel template for some of you who are not too familiar, with Excel. So use that template, but of course make sure you adapt it, to your needs. The numbers I've given you are just hypothetical, so make sure you adapt it to your needs. So you can do standard addition, calibration using the template that I've given you. And in this case, I've used method 3, where in the x-axis, I just add the volume. And the y-axis, of course, is the signal from the instrument. And then you can calculate, the residue deviations, by copying all these data as well as into this section so that you can calculate the deviations and so on. And based on that, you can calculate the m, which is the slope. You can get, the b, which is the intercept. And when you use these equations, typically that is what you call the least squares method. All right, method. And this is where you generate the equation of the line, the y is equals to mx, plus b, just by calculating the m, and calculating, the b. And so when you do the lab, you just need essentially to populate, the template, with the numbers that you get in the lab here and here, and it's going to automatically generate for you the m and the b, and that becomes the equation of the line. All right. It's also going to generate for you the standard deviation, of the x, which is this. Okay. So when you do the y is equals to mx, plus b, and you calculate, what x is, it's gonna give you the standard deviation, of your x, which is what you're looking for to calculate the unknown. Okay, again, make sure you know what you're doing in terms of being able to play with the template. Change the numbers as you should. Maybe the only other thing that I should point out is this K. You know, this K refers to, which is right here, refers to the number of repeats for the sample. So if you analyzed the sample 10 times, the K becomes 10. The other things, you know, the deviation, the residual deviations, they are already inbuilt, you know, in the template right there. Okay. For the standard external calibration, again, remember you just need the X, the standard solutions, and the Y is the signal. And as I've explained, you know, you get the equation of the line, Y is equals to mx plus b. And you already know the Y, you know, for the external calibration, you know, which is right here. And if you substitute it, you get the X. You get the X. Okay, you get the X, and the standard deviation of that X is already right here, you know, which you can use. So fairly straightforward. And so that's all that I'm gonna say about standard calibration methods. You know, the three methods: external standard calibration method, internal standard calibration method, and standard addition calibration method.